let's talk about editing and snapping. Editing refers to when we take existing features and we either modify those features or update them or create new features. So in this example here, it could involve moving this intersection, which is misplaced here currently in the GIS, and moving it to this location here. This may require editing a number of different lines and possibly different points along those lines in order to make it best fit along these dashed lines. So in editing, we're either creating new features, modifying existing features on the map, or we might be editing the attribute table as well. So in this example here, once again, we're moving a bunch of streets. That would be an example of modifying existing spatial features. So one thing we have to consider when we do all this is the topology. The topology refers to the spatial relationship between features, and it's kind of the logic of how GIS works, so it's important that we get this right. For example, these two roads were drawn here, and they're supposed to connect, but they don't. And that's because when someone was digitizing it, they just stopped a little bit short of that road. They might have even thought they were on the road, but they weren't. So we have something here called a dangle node. And a dangle node is just a node at the end of a line that's not connected to another line. And of course, this can be corrected by grabbing this dangle node and putting it right on top of this line. In this way, we're going to have a logical consistency where someone driving down this road knows that they actually connect up with this road, and they can just turn right and be or left and be on that road. In a similar way, sometimes polygons are drawn and polygons next to each other are drawn as two different polygons. And then in this example here, we can have these type of topological errors. These were not intended, but we have a gap between these two polygons here, and we have an area of overlap between these polygons here. And once again, in editing and considering the topology, we can correct this so that we have an orange polygon here, a blue polygon here, and then we have one line that they're sharing, which is this coincident line here. So we would have a coincident boundary now between two polygons instead of two different separate polygons that have these errors. The sliver polygon, this would be sometimes called a sliver polygon, this area of overlap all the way along them. So we want to have this logical consistency based on topology. One important way we can achieve this is by looking at snapping. So snapping is, as we're drawing a new line, how it's going to connect to another line that already exists. And of course, these connections can happen, for one example of a place would be at nodes. So one thing we can do is we can set our snap tolerance. And our snap tolerance is basically the distance of the interaction that will take place. So that if I'm digitizing and I click anywhere within this dotted circle here, it will automatically snap to this only node that exists within here. So if I'm digitizing line B, it automatically snaps to this position here. If I'm digitizing line C and I click here, it's not going to snap to this node because I'm outside of the snap tolerance. So in the end, we're going to have something nice and clean that looks like this. A is connected to B, but C is not connected to A and B. And once again, we can adjust this. If we do want C to be connected, we can make a larger snap tolerance, and that would just be changing a setting so that the snap tolerance is larger. And we can snap to anything we want to. In the last example, we snapped to a node. That's often done. We're drawing a new line here. We want this node to be the same as the node that's the endpoint of this line here. But sometimes we just want to snap to anywhere on a line. For example, these two lines are perpendicular to each other. We don't happen to have a vertice there, so we just snap right onto the line there. And if you remember, anytime we have a line, the two endpoints of the line are going to be nodes, and any point along the line that defines its shape is going to be called a vertex. So in this case here, we can also snap a node to a vertex. And for all of these, we would have some sort of snapping tolerance set, whether that's to this node here, to anywhere on the line that we might put a point to, or to one of these vertices. So we can have end snapping to nodes, edge snapping to the line, or vertex snapping to any of the vertices that make up another line that we're digitizing to.